Alright, so now that we have a good understanding of what significant figures are and how to determine how many significant figures a number has, we can now get into calculating. So remember, significant figures are important because they tell us how limited our measurements are. We don't want to report answers or calculations to an unrealistic level of accuracy. We want to make sure our answers based on calculations are keeping those limits within mind. So with that being said, there are two sets of rules when it comes to significant figures. It depends on what you're doing, whether you're adding and subtracting or whether multiplying and dividing. 90% of the time in chemistry, you'll probably be you'll probably be multiplying or dividing. Nevertheless, adding and subtracting does happen, obviously, and it does have a different set of rules. So we want to make sure we keep that separate. So if you are adding and subtracting values, the rule is you want to express the answer with the lowest number of decimal places. So if we take a look at the example that is shown, we see this first number has 2 decimal places, the second number has 3 decimal places, and the third number has 3 decimal places. So 2 decimal places is the lowest. And so when we get our answer here, we need to make sure we round it so that way it is expressed with 2 decimal places. So we would drop the 4 here. FYI, if this had been a 5 or greater, we would round that up to 9.22. And then, like I said, most of the time you'll be multiplying and dividing. And so the rule for that is when you are multiplying and dividing, you want to express the answer with the lowest number of significant figures. So we don't look at just decimals, we look at the whole number. So this first number is 3 significant figures. This second number is 5 significant figures. And this third number is 2. Because remember, zeros that begin the number are never significant. And so when we get our answer, the lowest number of significant figures was 2. And so 45.0118 would need to be rounded to 45. As a reminder, even though these examples didn't show, as a reminder, you would want to make sure that you have your appropriate units as well. In these examples, units were not shown, but we're going to see some examples where units are shown in just a few moments. A little note about rounding. I mentioned it a little bit, but when you are doing your calculations, first perform the calculation. Then you would want to determine the proper number of either sig figs, if it's multiplying and dividing, or decimal places if it's adding and subtracting. Be sure to look at the next digit past the significant digit that you're supposed to round to. And like I said earlier, if the number is greater than 5, you would want to increase the last significant digit by 1. But if the number is less than 5, keep it as is. A little note about this now, and I'll talk about it later too, is when it says perform the calculation, what you would want to make sure you do is do all of the calculations. So let's say, for example, you had, one number times another number divided by a number. You would want to make sure do all of that calculation first before you actually do your rounding. And we'll get into that in a few slides as well. As mentioned earlier, here's additional examples of how the significant figure rounding rules play out. And in this one, you'll notice that there's units. So notice what happens. When we are adding, remember the rules for adding, it's lowest decimal places. So this number has 2 decimal places. This one has 4. So we need to have our answer have 2 decimal places. Here's the unrounded number. We would want then round that to 37.35. Notice because 2 decimal places was where we needed to round, the next digit is a 4. That would not round it up. So we can just drop those digits. That's me crossing it out. And that's where we just get the 35. When you're adding, make sure your units are the same. You can't add a centimeter to a millimeter, right? So you need to make sure the units are the same, but your units will be retained. Same thing with subtraction, lowest decimal places. So if we were to subtract these two numbers, 2 decimal places, 4 decimal places, our lowest number is 2, and so this needs to be rounded to 2 decimal places. Notice the 2 decimal places is the 2 and the 4, but this 6 is going to make this round up to 8.25. Once again, units are conserved. When you're just adding and subtracting, the unit stays the same. When you're multiplying, different set of rules. Lowest sig figs. So 22.80 is 4 sig figs, and then 14.5540, that's 6 significant figures. So the lowest number is 4. And so this is the answer. When we round that to 4 significant figures, that ends up becoming 331.8. The 3, 1, and 2 were just simply dropped. But notice what happened to the units. when you take a centimeter times a centimeter, it actually now creates centimeters squared. So always watch what's happening with your units, especially with multiplying and dividing. One more example real quick. 4 sig figs here, 6 significant figures here. We are dividing, and so it needs to be lowest number of sig figs. If we think about how to round this number to 4 significant figures, we have the 1.566, but then this 5 is going to round that 6 up to a 7. Notice when you take a centimeter divided by another centimeter, the centimeters cancel, and so notice how this number doesn't have any units. So always make sure you're catching what's happening to the units as well. Example 8 is just another example of your rules, and so I have the answers here. You can actually go and update your notes and make sure you understand that. Notice the rounding rules, but then also the units as well. So just it's another example of that. We've done plenty in the video, so we don't need to cover that more. Now, a little bit more about rounding, okay? Because questions always get brought up, when do you round? Okay, in order to make sure that you avoid rounding errors, you want to make sure you always keep track of sig figs, but do not round until the very end of the calculation. That's important, okay? And that's kind of every time you round on a step of the problem, that's when you just get further and further off from the final answer. It's called propagation of air. An example of that would be, this is a really bad example, but it might make sense to you. Let's say I was 5'10 and a half, and I'm like, okay, well, we might as well round up to 5'11. Well, then if I'm 5'11, well, I'm practically 6 foot, keep rounding. Pretty soon I'm telling people I'm 6 foot when really I'm only 5'10 and a half, but the way I'm rounding, it just makes it seem like I can do that. But that's what's called propagation of error. Our final answer ends up being further off than really what the original answer was. And so what you'd want to do is don't round until you're done with the calculation. Because multiplying and dividing both have the same set of significant figure rounding rules, then that means do all your multiplying and dividing all in one step. You don't have to worry about your significant figures along each step. Just save it all to the very end. So an example of that is we have some values over here, right? We have f equals 2.54, g equals 7.63, w equals 4.70. These are just arbitrary variables. But if you notice, let's say you're doing a calculation where you first have to multiply f times g, which would give you an answer p. You would take that answer and go to step 2, which is then multiplying it by w to end up getting an r. Once again, these are just made up variables. This doesn't mean anything. But the point is that I'm showing you is what would happen if you rounded, based on sig fig rules, what if you rounded each step? So in other words, do step 1, get your answer and round p, and then take that rounded answer and then plug it in for step 2. Well, if you did that, f times g is 2.54 times 7.63. That's 3 sig figs, right? So if we rounded it to 19.4, which is 3 sig figs, and then put that answer in to multiply by the value of w, your answer would end up being 91.2 centimeters cubed. But what if we had waited, since step 1 and step 2 are both multiplying, what if we had waited to the very end to do all of our rounding? Well, then that means this first step, when we multiply, we're going to keep the whole answer, or at least go beyond. You don't have to keep the whole answer, but since I know 3 sig figs is what my answer should have been, go a few extra sig figs out. What if I just kept it to 19.3802? Plug that in, and then multiply it to get my ultimate final answer. If I rounded this ultimate final answer to 3 sig figs, my answer ends up being 91.1, which you may think is not that different from 91.2. You're like, it's only a tenth. And at Gen Chem 1, I can see why you would think that. But if you're going into the engineering field, if you're going into the medical field, that tenth can make a difference. And so we want to make sure we keep all of our rounding until the very end. All right. To wrap up, we have a few more slides left here. To wrap this section up, there are some times where you are going to be doing a calculation where there's actually both sets of operations, meaning there's adding and subtracting along with multiplying and dividing. An example of that is where you have to calculate a percent error. Percent error is something that we calculate in the lab to determine how much error or how far off we are from the true value. To calculate percent error, we would take the theoretical value, which is the value the accepted value, it's the value that you're supposed to get, minus your experimental value, that's what you get, divided by the theoretical value again, times 100. And think about it. If these two numbers are the same, theoretical and experimental, meaning what you got in the experiment is the same as theoretically what you should have gotten, then this top value will end up being 0, which then 0 divided by any value is still 0. So you'd end up getting a 0% error, which means that's what we want, right? We don't want any error. So that's good. That's what percent error is. But the point of this slide is, how do you deal with the sig figs? Because look, you have to subtract first and then divide. You have two sets of rounding rules. You have rounding rules for subtraction, but then you have rounding rules for division. How do you take care of all that? Here's the steps. You want to make sure you take care of the one set of rules first, but don't implement the rounding until the very end. It's best to show you an example. Let's take a look at this example here. Let's say I was calculating a density. That's what the grams per milliliter is. But let's say I was supposed to get 8.641. That's my theoretical value. But I did the lab and I ended up getting 8.43. How would you calculate this percent error using sig figs? Because the calculation's easy. It's the sig figs that's hard. Okay, first thing I would do is I would do the subtraction. So I'm going to do 8.641 minus 8.43. Now the answer that I get, just simply by calculating, I'm not doing anything rounding, is 0.2111 grams per milliliter, right? Because grams per milliliter is still retained when you subtract. Now, what's the next math step I'm going to do? I did subtraction. What's the next thing I'm going to do? Division, right? So I'm about to switch from subtraction to division. And since they have separate rules, I need to think to myself, okay, what should this have been rounded to? Based on subtraction, what should 0.211 have been rounded to? Well, if I take a look at my numbers, this number had 3 decimal places, this one had 2. So really, this number should have been rounded to 0.21. But I don't want to round yet, right? Because if I round now, that's where we get that propagation of error. That's where we get all those rounding errors. So here's what I do. It's a trick. What you do is you say, okay, I want to remind myself this should have been rounded to 0.21, 2 decimal places. So I put a bar over that digit right there. It reminds me that's where it should have been rounded, but I don't want to round yet. So now, that's what my top value is. I need to still divide it by 8.641 grams per milliliter on the bottom, and then multiply by 100. Now at this step, the two math operations that are left are division and multiplication, which, since they have the same rules, do everything. So I'm going to do 0.211 divided by 8.641, and then multiply by 100. When you're dividing, remember the rules there is its lowest number of sig figs. This number on the bottom has 4 sig figs. How many sig figs does the top number have? Be careful. You might be tempted to say 3 sig figs, the 2, 1, and 1, because remember, beginning zeros don't count. But remember, I should have rounded this top number to be 0.21. So really, because of that bar, that's to remind me, okay, that top number actually would have had 2 significant figures. So then this value would be dictated by the lowest sig figs, which is 2. The 100 does not need to be taken into consideration with significant figures. The purpose of multiplying by 100 is simply to take it from a fraction to a percentage. It's not the 100 is not a measured value. It's an exact value. So that means 2 significant figures is what my answer should be with. So when I take these two numbers divided by each other and multiply by 100 with 2 sig figs, I end up getting 2.4, and then it's a percent because the grams per milliliter cancel, and multiplying it by 100 is what makes it a percent. So 2.41% is my answer. The last slide here just talks about the difference between accuracy and precision. It sounds the same, but there is a slight difference. Accuracy is how close you are to the true value. If I hit a bullseye once, I am accurate. Precision is how close my multiple measurements are to each other. So right here, these measurements are precise. They may not be very accurate because I'm missing the mark, but they are precise because I keep hitting the same area. These 3 are neither precise nor accurate. So accuracy is when you hit the true value, and technically you only need one data point to hit the true value. Precision is how close a group of measurements are.